Bismillahirrahmanirrahim. Assalamu alaikum dear students. Welcome to the fifth lecture of Discrete Structures CSC 102. In the previous lecture we were discussing about logic gates, and we have discussed several basic logic gates and how to construct circuits using logic gates. We have also discussed designing circuits for given input-output tables, and we have discussed also equivalent circuits and how to reduce circuits. Today we shall also start with the reduction of circuits, as in the previous lecture we haven't discussed it much, and also in today's lecture we shall discuss NAND and NOR gates. We shall also discuss the Boolean algebra, decimal and binary representation of numbers, and how to add these numbers. And on the basis of these we shall discuss half adders and how to construct a circuit using half adders, and then full adder circuits. And with the help of half adder and full adder circuits we can construct parallel adder circuits for the binary addition of numbers, for the addition of binary numbers. So how to reduce a circuit or two equivalent circuits? For example, if we are given a Boolean expression, this one, P and not Q, or P and Q and whole and Q, and this is a Boolean expression, and we can construct a truth table easily and the corresponding circuit. How to construct the circuit we have discussed in the previous lecture. We just write here P and Q, and then we draw the circuit by watching this Boolean expression. For example, here we have P and not Q, so first we draw a line P which correspond to P, Q, and here we constructed a NOT gate, and then this line goes to AND. Now this represent P, here we have not Q, so here we have P. So this is we construct an AND gate here which gives us P and not Q. So this is, we have solved the first bracket here. Now we have another bracket P and Q. We connect here another line for the second bracket here and for Q also, and we insert them here in the AND gate. We obtain here P and Q. Now both of these are connected with OR gate, so we draw a line which comes out from this and from this gate, AND gate, and we have constructed here an OR gate. Here we arrived, and this represents basically this whole bracket, which is P and not Q, or P and Q. This is our whole bracket until here. Now we have another input here and we have conjunction of this whole bracket with Q, so we need another Q, so we draw another line here which comes out here, and we have AND conjunction operator here between this whole bracket and Q, so we give input here and we constructed an AND gate here, so which represent this here. This represents this whole bracket and Q, that is P and not Q, or P and Q whole bracket and Q. So this is our R. So this is how we can construct. We have discussed it in the previous lecture, how to construct circuits if we are given Boolean expressions. Now sometimes in Boolean expressions there are some certain simplifications. We can simplify Boolean expressions using the laws of or rules of logic, just like we have discussed in previous lectures: distribution law, commutative law, associative law, idempotent law. So such type of laws or rules of logic we can use to simplify such you can say that such long and complex Boolean expressions. So here we try to simplify this expression using the rules of logic, and then we see what happens. So here we consider the left hand side, P and not Q, or P and Q whole bracket and Q. Here if you look at this carefully, we can see that here we can apply a distributive law. Here we have P and not Q, or P and Q. So here we can apply a distributive law which gives us P and not Q or Q, because distributive law is basically P and Q or R, you can say this. So this is equivalent to basically P and Q or P and R. So this is basically this is distributive law we have discussed in the rules of logic. So if we are given this, we can write this, and if we are given this, we can write this, because it's we have proved it already. So we can use here distributive law, and we can write this whole expression into this expression. Now here we have not Q or Q. So not Q or Q is basically, or before this we can interchange their positions. We can write Q or not Q by using commutative law, as the commutative law was P or Q is logically equivalent to Q or P. And we know that by negation law, Q or not Q, or we have discussed it like this, P or not P is equivalent to tautology. Tautology is basically a proposition which is always true. We have discussed it in previous lecture. So Q or not Q gives us tautology, and this is basically a negation law. And we have also the identity laws, in which we have discussed that P and T is always equivalent to P. It is identity law. So P and T here can be written as P, and we have and here Q, so P and Q. You see here by using rules of logic, laws of logic, we can simplify long and complex Boolean expressions into, and we can by applying these laws we can simplify these expressions. Now this expression this whole expression is logically equivalent to this expression P and Q. It means that truth table of this expression and this expression will be identical, as we have discussed in the definition of equivalent circuits, that two Boolean expressions or two circuits are said to be equivalent if their truth tables are identical. That is, the truth values in each row, you can say in each row will be identical. So the circuit corresponding to this Boolean expression will be equivalent to the circuit given by this expression. So we can say that the previous circuit which we have constructed by looking at this Boolean expression, this is basically logically equivalent to this circuit. So we can conclude that if we are given long and complex Boolean expressions, if we first try to simplify these Boolean expressions by using laws of logic, we can simplify them, and then we can construct circuits, very simple circuits. So this circuit is logically equivalent to this circuit. You can see that this circuit is very simple. It contains only one logic gate, which is AND, and here in this circuit we have several logic gates, and it looks like a complex circuit, but it is logically equivalent to this. So this is how we can reduce circuits by using laws of logic. Let's consider another example for the reduction of circuits or equivalent circuits. Here we have another circuit. Find the Boolean expression for the circuits. We have to find the Boolean expression first for the given two circuits A and B, and then show that we have to show that they are logically equivalent. So there are two ways to prove that these two circuits are logically equivalent. The first is find the Boolean expression for both circuits. What will be the Boolean expression for the first circuit and for the second circuit? Then by using rules of logic, laws of logic, we prove that this Boolean expression is logically equivalent to the Boolean expression corresponding to this circuit. So this is the first way, which we have done in the previous example. We have proved here this Boolean expression is logically equivalent to P and Q. So this is the one way. What is the other way? Construct the truth table for both circuits. For the first circuit A, for the second circuit B. We construct the truth table by looking at this circuit, and then truth table for this circuit. If the truth values of both truth tables of these circuits are identical, then we say that these two circuits are logically equivalent. So first we write the Boolean expressions. Here we have AND, we have P, we have Q. The input of this AND is P and Q, so we arrive at here P and Q. Now here the input of this gate AND is P. Here we have not logic gate, so here we have not Q. The input of this logic gate is not Q, so here we have arrived at P and not Q. So here we have another bracket, here we have a bracket. Now the input of this logic gate is basically both. Here we have not P, here we have not Q, because here we have not gate on both these inputs. So at the end here we have not P and not Q, so we have another bracket here, another gate here OR, whose input is this, this and this. Here we have P and Q, here we have P and not Q, here we have not P and not Q. So here we have OR gate, therefore we can write P and Q or P and not Q or not P and not Q. So here we have this, so this is basically the Boolean expression which corresponds to this circuit. You can see that this is very long Boolean expression, and the Boolean expression corresponding to this circuit, here we have one logic gate OR, and here we have another NOT gate. So here we have not Q, here we have P. So output of this circuit is P and not Q. So we have to prove that these two Boolean expressions are logically equivalent, or we can, I told you that we can show it by using truth tables. First we prove it by using by proving this Boolean expression is logically equivalent to this Boolean expression. Here we consider the left hand side, P and Q or P and not Q or not P and not Q. So this is basically the left hand side of the, or you can say this is the Boolean expression corresponding to circuit A, and we shall prove it equivalent to the Boolean expression to the circuit B. So we consider this. Now if we look at this Boolean expression, we can see that here P and Q or P and not Q, we can again use the distributive law here as we have used in the previous example. So we have used here the distributive law. We obtained P and Q or not Q, or here the rest will be same. here, not P and not Q. So Q or not Q is basically a tautology, as by using negation laws, and we write P and T is a tautology. P and T is equivalent to P by using identity law. So here we have P or not P and not Q. So we can use here a distributive law. We can write P or not P and P or not Q. Here P or not P is basically a tautology by using negation law. Then tautology and some proposition. Here you can see that we can say that P and some logical, some proposition any. You can say this is R, which is R is here basically P or not Q. So T and R is logically equivalent to basically R, because by using negation law. So we can write here T and P or not Q is equivalent to basically this, or by first by using commutative law we can write it as this here and tautology here, and this is logically equivalent to this. So what is this? This is basically the second circuit B circuit. This was our A circuit, which we have considered in the left hand side. So you can see here by using rules of logic we can simplify such type of long Boolean expression into a very simple and short Boolean expression. So we can say here that this circuit is logically equivalent to this circuit. The output of these circuit will be same. Next we start what are the NAND and NOR gates. We have I have introduced these gates in the first lecture, in the first lecture when we have started, not exactly in first lecture, but when we have started the logic gates. In the start of logic gates I have introduced you NAND and NOR gates, but I haven't discussed it. So now we discuss what are NAND and NOR gates and how these gates help us to simplify the complex and long Boolean expressions, and what are the application of these gates. Another way to simplify a circuit is to find an equivalent circuit that uses the least number of different kinds of logic gates. Two gates not previously introduced are useful for this. That is, these gates also help us to simplify, to reduce the complex and long Boolean expressions into simple Boolean expressions. First is a NAND gate is a single gate that acts like an AND gate followed by NOT gate. That is, first we apply AND and then NOT gate. It will give us an AND gate. The expression, symbolic representation for the NAND gate is this. Basically, this is basically the combination of AND and NOT gate. So this is, you can say, NOT plus AND gate gives us NAND gate. The input of this gate is basically P and Q, 1 1, 1 0, 0 1 and 0 0. And outputs, what are the outputs? The output signal of a NAND gate is 0 when and only when both input signals are 1, and output signal for basically here the logical symbol corresponding to these gates are this. This is the logical or the symbolic representation of NAND gate. That is, we write this P, this vertical bar, you can say that P NAND Q is logically equivalent to NOT P and Q. That is, this is basically an AND gate followed by a NOT gate. So first we apply P and Q and then we apply NOT gate. So we represent symbolically it as P NAND Q, and this is basically logically equivalent to, by using the definition of NAND gate, NOT P and Q. And the truth table for this gate is PQ11 and these values, and its output is basically P NAND Q. When both P and Q are 1, the output of this gate is 0. How? As this P NAND Q is equivalent to not P and Q. When P is 1, Q is 1. P and Q is 1. When we apply not on this will give us 0. So therefore here the first output of this gate is 0. When P is 1, Q is 0, we have P and Q 0, and then we apply not, we get 1. Similarly, this is 1, this is 1. So this is basically a NAND gate. And next, what is the NOR gate? A NOR gate acts like an OR gate followed by NOT gate. That is, if we add up OR plus NOT gate, that is NOT plus OR, this will give us NOR gate. And its output, what are the outputs of this gate? Output signal for a NOR gate, this is basically NOT plus OR and NOR gate. It's basically the abbreviation of NOT plus OR, NOR. Its logical or symbolic representation is basically this, the down arrow, this, which is called a Pierce arrow, and this vertical line, or you can say that this vertical bar is called a Schaeffer stroke. We can read it as also P Schaeffer stroke Q is logically equivalent to P and Q, and P Pierce arrow Q is logically equivalent to not P or Q. As we have discussed here, this NOR gate is basically OR gate followed by NOT gate, so this is logically equivalent to this by the definition. And the truth table for this logic gate is basically this, and the symbolic representation, the gate corresponding to this NOR gate is this. This is basically OR, and we draw a small circle here after the OR gate. Similarly here in the NAND gate, we construct an AND gate and we draw a simple circle here. In the AND gate, this will give us the gate representation of these logic gates, NAND and NOR. The truth table for this NOR gate is basically the inputs are to PQ 11 10 01 00. We write it as R or P Pierce arrow Q is basically 0 when both of these are 1. You can draw yourself the output here, input or truth table here, as P Pierce arrow Q is basically logically equivalent to not P or Q. When P is 1, Q is 1, P or Q is 1, when we apply not, we get 0. When P is 1, Q is 0, P or Q is 1, when we apply not, we get 0. Similarly 0 1 0, when P is 0, Q is 0, P 0, Q is 0, P or Q is what? This is 0. When we apply not, we get 1. The truth table, the truth value of this logic gate. So these are the truth table for these logic gates. Now it can be shown that any Boolean expression is equivalent to one written entirely with Schaeffer strokes or entirely with Pierce arrows. That is, if we are given any expression, any Boolean expression we have considered in the previous two examples, we can write any Boolean expression by only using Schaeffer strokes or by only using Pierce arrows. That means any digital logic circuit or any Boolean expression which correspond to digital logic circuit is equivalent to one that uses only NAND gates or only NOR gates. So we consider some examples how to express Boolean expressions by using Sheffer-Stokes or Peirce arrows. For example, let's consider very simple Boolean expression not P. Here we have not P. For example, not P. How to write this Boolean expression by using only Sheffer-Stokes or Peirce arrows. And Sheffer-Stokes, basically the definition of this Sheffer-Stoke is P Sheffer-Stoke Q is logically equivalent to not P and Q. This is what the definition of Sheffer-Stoke or NAND gate. Now how to express this not P by using expressions of such type which uses only Sheffer-Stokes. This is what we have to write in this next example. Not P is basically, we can see not P is logically equivalent to here not P and P. That is, we can write not P and P, and you know that P and P is logically equivalent to P. We have discussed it in the rules of logic or laws of logic. So we can write P as P and P, not here, we have already not. Now instead of Q we have P here, instead of Q we have P here. So we have to construct here, we try to construct here the definition of Sheffer-Stoke to convert this Boolean expression into an expression which contains only the Sheffer-Stokes. So here we have not P and P, and instead of Q we have P here, therefore we can write it as P Sheffer-Stoke P. So not P is a Boolean expression, and this is logically equivalent to this, and we have converted it into a Boolean expression which uses only the Sheffer-Stokes. Similarly, we can consider this example, P or Q. P or Q is basically logically equivalent to not of not P or Q, as we can, by double negation law, we have not P of not P of not P is basically logically equivalent to P. We can write it as, this is basically negation law. So here we can write P or Q as not of not P or Q, which is the double negation law, and then we can apply the negation on this by using De Morgan's law. Not P or Q is logically equivalent to not P and not Q, and then by using the part A here, as we know that not P is logically equivalent to this P Sheffer-Stoke P. Here we can write not P as P Sheffer-Stoke P, and this remains same here, and not Q similarly by using part A we can write as Q Sheffer-Stoke Q. Now here we have this expression not P Sheffer-Stoke P and Q Sheffer-Stoke Q. This, if we suppose that this is R, this is W, then we have not R and W. So by using the definition of the Sheffer-Stoke, we have P and Q, not P and Q is logically equivalent to P Sheffer-Stoke Q. So we can write it as R Sheffer-Stoke W. Now what is R? R is basically this P Sheffer-Stoke P, and W is Q Sheffer-Stoke Q. So we can write it as this is logically equivalent to P Sheffer-Stoke P then shuffle stroke and Q shuffle stroke Q. So this expression here, P or Q, is logically equivalent to this. So we can write any Boolean expression by using only the shuffle strokes, or we can convert any Boolean expression into an expression which uses only the shuffle strokes. So now we consider the same example for and we convert the same Boolean expressions into Boolean expressions which contains only the Peirce arrows which is a downward arrow. It's just a notation, and the definition of Peirce arrow Q is basically logically equivalent to not P or Q. Here in the first part, here not P by using the same logic, not P but little bit different. Not P is logically equivalent to not P or P, because in this definition we have or, so we can write here P as P or P by using the rules of logic. Now here we have a P instead of Q, so we can write it as P Peirce arrow P. So not P is logically equivalent to P Peirce arrow P. So this is done. Now we consider the second part, B part, and we have to write P or Q. We have to prove P or Q is logically equivalent to P Peirce arrow Q bracket Peirce arrow bracket P Peirce arrow Q. So this is what we have to prove, and we prove it either by considering left hand side to right hand side, or we can start from right hand side and we can arrive at left hand side. I have used the right hand side here just to, but you can use left hand side also by reversing the steps. If we consider P or Q, for example, P or Q, then we can write it as not of not P or Q by using double negation law. This is basically the definition of Peirce arrow, not P or Q. So what is this? This is basically P Peirce arrow Q. Now by using part A, that is not P is P Peirce arrow P. So here we have not, consider it whole as a P, so we can write as P Peirce arrow Q bracket, this is P Peirce arrow again P Peirce arrow Q. So this is how we can prove it, and similarly you can prove the part C also. We can convert it P and Q into a Boolean expression which contains only the Peirce arrows. Next we start Boolean algebra. Before starting the Boolean algebra, we repeat some decimal representation which I hope you have studied in your early classes, 6th, 5th, 6th, 7th. So what is basically the numbers which you see in daily life? For example, 6152. What is this number? Actually this number is basically a decimal representation. Deci means 10, and this is basically a Latin word. Decimal comes from the Latin word deci, which means 10. This is basically a system of numbers whose base is 10. So its decimal representation is, we can write 6152 as 6 into 1000 plus 1 into 100 plus 5 into 10 plus 2 into 1. And then 1000 can be written as 10 power 3, 100 can be written as 10 power 2, 10 can be written as 10 power 1, and 1 is basically 10 power 0. Any number power 0, if we have some number which is real number, its power 0 is always 1. A could be anything. So if we write A is equal to 10, 10 power 0 is 1, or 2 power 0 is again 1. Any numbers power 0 is equal to 1. So more generally, or you have also studied that this is unit place, this is 100, this is 1000, this is unit place, this is 10th place, this is 100 place, and this is 1000 place. Unit, this is 10th place basically, this is 100, and this is 1000. So more generally, any number and decimal number, this can be written as sum of product of the form d into 10 power n, where d is any non-negative integer. Here it could be 0, 1, 2 up to 9. So that is, any number is basically sum of the products of this form. We can write any decimal number like this. How to convert, and there is another binary notation which you have studied in your early classes. Binary notation, I repeat here, how to convert a decimal number into a binary notation. For example, here we have 27. Usually in decimal representation we write 27 base 10, we like this, but in decimal numbers we don't care about this base, because it is obvious that the base is 10 when we use daily life mathematics or calculations. Here 27, how to convert it into a binary expression. 27 can be written as 16 plus 8 plus 2 plus 1. So here 16 can be written as 1 into 2 power 4 plus 8. Here 8 can be written as 1 into 2 power 3, and 2 can be written as, here we have a missing number here, another, we write here 0 into 2 power 2 plus 1 into 2 power 1 plus 1 into 2 power 0. Here we have two increasing powers of 2. Here we have 2 power 0, 2 power 1, 2 power 2, 2 power 3, and 2 power 4. Here in this expression we didn't have the 2 power 2, so we write it 2 power 2 into 0. Now the coefficients of these powers, 1, here 1, here we have 0, here we have 1, here we have 1. So the coefficient of these increasing powers of 2 is basically, we can write them here 1, 1, 0, 1, 1, and the base will be, the base of this number will be 2, and this is basically the equivalent form of this 27 into a binary representation. Just to remind you, the powers of 2, 2 power 0 is 1, 2 power 1 is 1, 2 power 2 is 4, 2 power 3 is 8, 16, 32, 64, 128, this. So we can represent any decimal number, we can convert any decimal number into a binary number or binary representation, and similarly we can convert any binary number into a decimal representation. Here are the first 9 decimal numbers, the conversion of first 9 decimal numbers into the binary representation. 1 base 10 means the decimal representation of 1 is 1. We write it here in 1 base 10. This is 1 into 2 power 0. This is 1 base 2. 2 base 10 is logically equivalent to 1 into 2 power 1 plus 0 into 2 power 0, which is 1, 0. Similarly 3 base 10 is equivalent to 1, 1 base 2. 4 base 10 is 1, 0, 0, 2 base 2, and similarly you can see the other integers. The binary representation is given here. Now how to convert a binary number, a binary representation of numbers, into a decimal representation of number. Let's consider this example. Here we have this number which has base 2, that is, it's a binary number, that is binary representation of some number. How to convert this number into a decimal notation? Here, as we have converted a decimal number into binary, we reverse the same process. We start by this, we write 1 into 2 power 0, the next number into 2 power 1, next number into 2 power 2, next number into 2 power 3, next number into 2 power 4, and the first number last, you can say, number into 2 power 5. So here we don't miss any power of 2. We don't miss any power of 2, that is 2 power 0, 2 power 1, 2 power 2, 2 power 3, 2 power 4, 2 power 5. As we have written here, when we have converted a decimal number into binary notation, if some power of 2 is missing, we can write it, this power, by multiplying it by 0. We don't miss any power of 2. So this is a very important point here. So here we write 1 into 2 power 0, 1 into 2 power 1. Here we don't have any power of 2. 2 power 2 we don't have here, so we write here 2 power 2 into 0. This will not affect our calculations, but this will give us the exact binary representation of this decimal number 27. So do not miss any power of 2. Similarly here, once you have written this expression like this, then just simplify this expression as you simplify the expressions in decimal representation. 1 into 2 power 5, 2 power 5 is 32. I have given you this table. 2 power 5 is 32, 2 power 4 is 16, 8, 4, 2, 1. So we use this table here and we write 32, 16, but here we have 0, so we don't write it because it is 0 into 8 is 0. So here we come to the next point, next number, 1 into 2 power 2, this is 4, and 0 into 2 power 1 means there is no 2 here. Here we have 1 into 2 power 0, this is 1. We add up all these numbers, we add in decimal numbers. 32 plus 16, 48, 50 plus 4, 52, and 1, 53. So the conversion of binary representation into decimal representation is like this. So this is given in the form of a table. We can convert binary representation numbers into decimal representation numbers. Now, how to add these numbers in binary notations? If we are given these two numbers, these in binary notation, this is base 2 here, not 2. This is base 2. Here we have 111 base 2, not 2. So add 1101 base 2 and 111 base 2 using binary notations. We have to add these numbers, but first we see how to add only 2 digits in binary notations, because 2 base 10 is equal to 1 0 and 1 base 10 is 1 2. So as here we have discussed, 1 base 10 is 1, 2 base 10 is 1 0, 3 base 10 is 1 1 base 2. So if you remember these 3 numbers, that will be enough in binary addition. So 1 base 2 plus 1 base 2 is basically 1 0 base 2, and similarly if we have 1 base 2 plus 1 base 2 plus 1 base 2, this is 1 1 base 2, as 3 base 10 is equal to 1 1 base 2. Or you can add first these two numbers, 1 base 2 plus 1 base 2 is 1 0 base 2, as in this, and then you can add this number here, 1 base 2, this is 0 plus 1 is 1 and 1 remains 1. this is 1 1 base 2. So this is how we can add only 2 digits or 3 digits in binary notation. Now let's add these two numbers. Here we have 1101, the first number. The second number is 111. We write the second number on the by starting the leftmost, or you can say that below the last digit of this whole binary digit. So we write it like this: 1101 and 111. We add up first two numbers here. When we add up these two numbers, 1 1, this will give us what? 1 0. We write here the leftmost number and we send the right number into a carry. We send this number as a carry to the next column, you can say this. Just like we add the numbers in the decimal representation. If we add up this 5 into 5 6 plus you can say 7, in binary, in simple decimal representation, we have 6 and 7 13. So we write 3 here, we send carry 1 here. So and then we add up this number 5 1. 5 plus 1 is 6. So this was basically the addition in decimal number. Now here in binary notation, when the sum of two binary digits reaches 2, we divide it by 2, as you have discussed. You have already read it in earlier classes. So 1 plus 1 is basically 2. In decimal representation, 2 base 10 is equal to 1 0 in binary representation. So now we write it here and we send this one as a carry here. So here we have now 1 plus 0 plus 1. Again we have 1 plus 0 is 1 and 1 plus 1 is again 2. Again we have 2 in decimal representation. We write it as 1 0. We write here again 0 and we send this 1 as a carry here. Now we have 1 1 1. This is basically 3 in decimal representation, and 3 base 10 is logically equivalent to what? 1 1 base 2. So we have 1 1 base 2. We write here 1 and this one we send as a carry. Again we have 1 plus 1 is basically 2. 2 base 10 is what? 1 0 base 2. Here we have 0. We send 1 as a carry, but there is no other number here, so we write 1 here also. So this is how we add two binary digits, two binary numbers. Now what is the application of this in circuits? We can construct circuits to add binary digits, and as you can see, as you know that in computers, the computer addition and computer adds the numbers first by converting them into binary numbers, and then it adds and it converts back to decimal numbers, because in computer we can use only the bit notation, that is binary numbers 0 1 1 0. So what is now the application of logic in the application of Boolean algebra in logic? Now just like Boolean logic, variables can only be 1 0 instead of true false. Logic we can interpret as Boolean algebra also. In logic we write true false, but in Boolean algebra we say 1 0. True is equivalent to 1 and false is equivalent to 0. So not what is the negation of 0? Negation of 0 is 1, as the negation of false is what? True, and negation of true is false. So negation of 0 is 1, negation of 1 is 0, or OR is used as plus. 1 plus 1 is 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is what? We have discussed it. This is basically 1 0. And is used as multiplication. 0 into 0 is 0, 0 into 1 is 0, 1 into 0 is 0, and 1 into 1 is 1. So this is how we can relate Boolean algebra with the logic. Now what is half adder? When we add up 1 and 1 here, we obtain basically, when we add up 1 1 we get 2. 2 is not allowed in binary numbers, only 0 and 1 is allowed. Therefore in computers, how to add such type of digits when we reach at 2? This is logically, basically this is equal to 1 0 in base 2, this is in base 10. To add such type of digits, we construct a circuit which is called basically a half adder circuit. In this, we consider adding two 1-bit binary numbers, x and y. 1 bit means only single digits. If we add up 0 plus 0, okay, 0 plus 1 is 1, 1 plus 0 is 1, and 1 plus 1 is 1 0. This is obvious that base is 2 here. This is binary representation. Now here the problem is, here if we add up 0 plus 0, it's 0, there is no problem. If we add up 0 plus 1, we'll get 1, there is no problem. If we get 1 plus 0, we get 1, there is no problem. But when we add up 1 plus 1, so there are two digits. One is called sum and the other is called carry. As we have in addition here, when we add up 1 and 1, we write here 0 and we send 1 as a carry here. So when we add up 1 plus 1, which gives us 2, here we have two digits. The first is called sum and the other is called carry, because this one we send as a carry. Now in half adder circuit, the input are xy, which could be 0 0, 0 1, 1 0, 1 1, which is false false, false true, true false, true true. When we add up 0 0, we have sum. This 0, when we add up 0 0, we can write it as 0 0 in binary notation. This is sum, this is carry. This is sum and this is carry. When we add up 0 and 1, we have 1. This can be written as 0 1 in base 2. Here 1 is sum and carry 0. This can also be written as 0 1 base 2. 1 is sum and 0 is carry. When we have 1 plus 1, we have 1 0. This 0 is sum and this 1 is carry. So this is we have explained, we have summarized all these calculations here in this table, which is 0 0 0 1 1 0 1 1. This is input. And what is the output? Output is also two integers. The first is sum and carry. If we add up 0 0, we get 0 sum, 0 carry. If we add up 0 and 1, we get sum 1 and carry 0, as we have discussed here. And when we add up 1 1, the sum is 0 and the carry is 1. The carry is basically obtained by using AND gate here. If we apply 1 and 1, we get 1. So carry is basically x and y, and sum here is basically x XOR y, that is exclusive OR. We have discussed this gate in the basic logic gates in the previous lectures. This is basically exclusive OR. This is XOR. We have discussed it, and its output is 1 when exactly one of P or Q is 1, otherwise it is 0. We have discussed it, the XOR logic gate or XOR notation, we have discussed it already. The circuit to compute this is called a half adder circuit. A such type of output, if we calculate by using circuit, this circuit is called basically a half adder. And the circuit is this, where the input is X and Y. By looking at the truth table here, we have X, Y carry sum, because as the outputs are also 2, so inputs are here. When we have both 0 0, we give input. When the sum is basically 0, we construct this circuit. Input is basically X, Y. We construct here OR gate. We construct here an AND gate. You know, this is basically an OR gate, this is an AND gate, this is also AND gate, and this is NOT gate. This circuit represents this input output table, or you can say truth table. When both X and Y are 0, we have 0 here, we have 0 here, we have 0 here, we have 0 here, we get 0 here, and we get 0 here, because here we have OR, here we have AND. We have NOT here, so we get 1 here, we remain 0 remains here, because here we have 0. We have AND gate. When both X and Y are 0, we obtain here 0, sum is 0, and carry. Here we have 0, here we have 0, here we have 0, this 0 comes here 0, so we get sum as a 0 and carry as a 0. And I explain you this, or when X is 0, Y is 1. When X is 0, Y is 1. We have 0 here, 1 here, so we get 1 here, and we have 0 here and 1 here, we get 0 here, so here we have 1, here we have 1, and this gives 1 here. So sum in this case is 1, and carry comes again 0. When both X and Y are 1, this is 1 and this is 1. We have 1 1, we get 1 here, we get 1 here, and NOT, when we apply NOT, we get 0 here, 1 and 0, and we get this give us 0 sum. We have 1 here, this comes again here 1, so carry is 1. So this circuit basically describes the sum of two single digit numbers, either 1 1, 1 0, 0 1, or 0 0, two digit numbers. And you see that when we add up two numbers in binary notations, for example, this number 1 1 0 0, 1 1 1 0, when we add up, we get 0 here, we get 1 here, we get 1 and 1 carry. When we add up now these three numbers, we get, we have problem. We cannot add three numbers here by using half adders. So to add three numbers by using circuit, we construct another circuit which is called a full adder circuit. That is, here half adder circuit, it can add up only two digit binary numbers. But when we have three numbers in the addition of any two binary numbers, when we add up, we have three numbers, there is a problem. We cannot add these three numbers by using half adder circuits, and for to handle such type of problem, we construct a full adder circuit which will add up three digits in binary, three binary digits. This can add up. The inputs are again X Y, output is sum, carry, out, and here input basically is now the third one. Also we have carry in. We have, for example, here we have this is input, and input is added with along with the carry also, carry. So when we have three binary digits, single digits, how to add up these numbers? So we suppose generally if we have 3 digits PQR, how to add these numbers, and such type of numbers are added by using half adder circuits. We use 2 half adder circuits and 1 OR gate to construct a circuit which is called a full adder circuits. The inputs are PQR and output is carry and sum. How to add 3 digit numbers, for example 1 1 1, 1 base 2 1 base 2 1 base 2. We add up first 2 numbers first, 1 2 plus 1 2, by using half adder, and we get 1 carry and 1 sum. We can, here in this case we have 1 0 base 2, 0 is sum and carry is 1, and the result of this number we add up in this number. That is, now this result is basically 1 0 base 2, and we add 1 base 2, the third number, in this the resulting expression. These 2 numbers will be added up by using half adders, and we get the first carry and first sum. Now the sum of the resulting expression will be added to the next digit. So this sum we gave here the input of another half adder circuit. We have R as an input, the third number here R. The inputs are 2, again 2 digits, and to add these 2 digits we again use an half adder circuit. This will give us another carry and sum. You can say carry 2 and sum 2. The carry 2, the second carry, will go here in the OR gate as the input, and the carry 1 here in the as the input of this OR gate, and the sum will come here as this will be the sum, and this will be the final carry. So this type of circuit is called a full adder circuit. This is used as basically to add up 3 binary digits. Now by using these 2 circuits, why we have constructed these 2 circuits, half adders and full adder circuits. Basically these 2 circuits are used for the addition of 2 boolean numbers, 2 binary numbers of any length. That is, if we have these 2 numbers in computer, how we add up these 2 numbers. First, at the first step we use a half adder circuit, and then we could have sum and carry here, and then at each step we need a full adder circuit to add up 3 binary digits. For the first case we use half adder, and for the other remaining cases we use full adder circuit to add up the 3 binary digits. So to construct a circuit, to add 2 binary digits of any length, binary numbers of any length, we can use half adder and full adder circuits to add up 2 binary digits of any length, and such type of circuits are called basically parallel adder circuits. For example, if we have any 2 expressions, binary expressions, PQR base 2 and STU base 2, these 2 binary numbers, we can take here also A, B, C, D, binary numbers of any length we can choose. And how to add these numbers? For the first 2 we use half adder, and for the remaining we use full adder, because we might have here a carry row here. So to add up these numbers we use parallel adder circuits, and the first, as I have told you, in the first column we use half adder, and in the next columns we use full adder circuits to add up 2 binary numbers of any length. For example, here to add up these 2 PQR and STU, here we have PQR and STU. To add RU we use half adder, and then we get one sum and one carry, and the carry will be added to the second column here, Q and T. Here we have carry 1, so carry 1 is added here with Q and T, and we have constructed a full adder circuit. We have one sum and carry. The carry in this case will also be the input of the full adder circuit. When we add up P and S, here we again have another carry, so this carry will be input here. We obtain sum and carry, and the sum, the result of the sum of these two binary digits will be the first sum in this case, sum in this case, sum in this case, and carry in the final case. So the sum of these two binary digits will be W, X, Y, Z. So this is basically the sum of two binary digits. We can add up like this by using parallel adder circuits, two binary digits of any length. I think it's enough for today. We stop here. So in today's lecture we have discussed equivalent circuits and how to reduce circuits into simple circuits. We have also discussed NAND and NOR gates, basics of Boolean algebra, how to add two binary digits, and how to convert binary into decimal and decimal into binary. We have discussed also half adder and full adder circuits, and we have discussed how to add two binary numbers of any length by using parallel adder circuits. In the next lecture we shall start the logic of predicates, quantifiers, and predicates, or you can say quantified statements. We shall meet in the inshallah in the next lecture. Until that, Allah Hafiz.